we're talking about Euler's method. And in this method, what you do is you start at the point that is indicated by your initial value, and you're going to proceed in the direction that is dictated by your slope field, just like we did in the first objective. And then you're going to stop after a short little period, which we're calling the step size and denoting that with a little h. And then you're going to change directions according to the slope at that particular point. So let's take a look at the math involved in this. Okay, so we need a differential equation, and that's what we have here. This is y prime is equal to a function of x and y. And remember, that gives us the slope at every single point in the plane. Okay, so h is going to be our step size. Most common step sizes could be a half, it could be a quarter, could be 3/4, maybe even a tenth. And that's going to tell us how far we're going to have to step to the right each step of the process. Okay, we're going to take our initial point that they would have given us, and we would take it and put it into our slope equation, our differential equation. Our initial equation, we're going to call that point x sub 0, y sub 0, and we just take that point and we put it into our slope equation to get our initial slope of f of x sub 0, y sub 0. So this is just like function notation, like f of x. It would be some sort of number, but this time it has x's and y's in it, but it's still some sort of number, which is the slope at that particular point, at the initial point. Now we're going to take these two pieces of information and pretend like this is an Algebra 1 problem and write the equation of the line. You only need a point and a slope, put it into point-slope form, and then solve it for y, and here's what it looks like. We've got y is equal to, and this y in this case is going to be what we're going to use in order to plug in y1, or actually to find y1. It's equal to y sub 0, that's my initial point, that's right here, plus f of x sub 0, y sub 0, that's my slope. It's some sort of number being multiplied times x sub 0, which is my initial x coordinate, right? It seems complicated, however, it's just point-slope form, all right? But we're going to simplify this process because we don't want to have to find this equation every step of the way and then plug in our new x value in order to find our new y value. So we're going to simplify this process a little bit. All right, so in order to find y1, we're going to stick in x sub 1 in for our x value, that's right here. And then we're just going to simplify it down. And it's going to tell us what y1 is supposed to be. So y1 is dependent upon the previous y value plus the slope times x sub 1 minus x sub 0. We just plugged in x sub 1 as our new point. And how do we get this x sub 1? We take the original x sub 0 and we add our step size to it. Maybe our initial point was 0 and our step size is a half. 0 plus a half is 0.5, and that's what we would stick in here. All right, but wait a second. Take a look at this thing that's this x sub 1 minus x sub 0. That should just be our step size, because in order to get x sub 1, we had to take x sub 0, the initial condition, and add our step size to it. So what I'm going to do is I'm going to replace x sub 1 minus x sub 0 with a step size of h, and it simplifies this just a little bit. Because what we need is a number. I don't need an equation. I just need the approximation, which is the function value at that particular point. So what we have here is y sub 1, that's our next point, our next y value, is equal to the previous y value plus the previous slope multiplied times our step size. Okay, so we're going to try to generalize this process here. This is, again, just our slope, the previous slope, multiplied times our step size. Okay, so all of this shows us, this slide in particular shows us that we don't have to use the equation every step of the way. You could, you absolutely could. If you get lost in the details on this, you could always just go back to point-slope form, plug in your point. But this is going to give us a more generalized method that's going to bypass that equation and just give us the number. All right? So here's the piece of information that we need. We need ourselves a step size. That's given to us in a problem. We need a differential equation, which is going to tell us the slope at that particular point. That's also given to you in the problem. And you absolutely need an initial condition, also given to you in the problem. The initial slope isn't. To get the initial slope, you just plug that into the differential equation. Okay, so now we want to compute y1. Before we can compute y1, we need x1. To get x1, it's very simple. It's the simplest part of this whole process. You take x sub 0 and add in whatever your step size is to get your new x value. To get your new y value, it's dependent upon y1 and it's dependent upon the previous slope, like this. y1 is equal to the original y value, y sub 0, plus our step size, whatever that happens to be, multiplied times the slope at our original point, x sub 0, y sub 0. Okay, so let's say that we wanted to find x sub 2. X sub 2 is going to be dependent upon x sub 1, where we add our step size to it. So it's just x sub 1 plus h. To find y sub 2, it's going to depend upon y sub 1 plus our step size, but this time it's not going to use the slope at 0, 0. That's the slope back here at this previous point. We want the new slope using x1 comma y1, and this is what it looks like. So it's our step value times the slope at the previous point. And then you generalize this. You just keep doing this over and over again to however many steps that you need in order to get your desired outcome. So in general, x sub n is equal to x sub n minus 1. That's the previous x value plus our step size, whatever that step size happens to be. To find y sub n, you use y sub n minus 1. That's your previous y value right there, plus your step size multiplied times the previous slope. The slope computed with the point that came right before it. And I know this seems like a very, in theory, a very complicated procedure, which will be made simpler by actually taking a look and working through one of these exercises. So let's look at example 8 here. Given that y of 0 is equal to 1, that's our initial condition, and dy dx is equal to x plus y, there's our differential equation, which is a function of x and y. What is the approximation for y equals 2 if Euler's method is used with a step size of 0.5? Okay, so I'm going to work through this one with you step by step. This is example 8. And we have a couple of things here. The first thing I'm going to write down is my initial condition. And it was 0, 1, I believe, yeah. Our differential equation, which is our slope equation, is dy dx is x plus y, I think, and it is indeed x plus y. And then one more piece of information that we need is our step size. That's denoted with an h, and this was 0.5. And what we're trying to find in this situation is y of 2. So how many times am I going to have to carry out this Euler's method process? If my step size is a half, and I'm starting at 0, how many times am I going to have to do it in order to get up to 2? Well, 2 divided by a half is going to give me 4. I have to do this 4 times since I started here at 0. The best way to carry this out is with a little table here. So in this table of values, the top row here is going to denote how many times I have done this process, which I will say is an n. And then we're going to have some x values. And then we're going to have some y values. And you'll probably need a calculator along the way. So our first one is, we haven't done anything. It's our initial condition. Our n is equal to 0. And that was given to us in the problem. It's 0, 1. Okay, nothing to do there yet. Now we're going to iterate this process once. So my new x value, I should say x sub 1 is basically what we're trying to find here, should be equal to the previous x value, which is this 0, plus our step size, which is this 0.5 right there, to get 0.5. So my new x value, x sub 1 is equal to 0.5. All right, so now let's do the same thing for the y value. The y value comes from the previous, so this is y sub 1 we're finding. We're trying to find y sub 1. We're going to take the previous y value, which is equal to 1, plus our step size, which is this 0.5 again, and multiply it times the previous slope. So the previous slope is determined by our slope equation, which is x plus y. So I'm going to use my previous set of points and go 0 plus 1. And now simplify this down. So that's just a 0.5. 0.5 plus 1, I get 1.5. In other words, I've got the point now, 0.5, comma, 1.5. Okay, so now here's my second go at this. The second go is going to take this previous 0.5 here and is going to add in the 0.5 for the step value. No coincidence. Total coincidence. And get 1. Here's my new x value. My x sub 2 is 1. Okay, so to find my y sub 2 is what we're finding next. I'm going to take this previous y value, which is 1.5. Add in the step size, 0.5. Multiply the slope computed at the previous point. That's this and this. 0.5 plus 1.5, because that's what our differential equation is telling us to do. All right, so 0.5 plus 1.5 is 2. 2 times a half is 1. 1 plus 1.5 is 2.5. All right, so far? So again, what we have is the new point, 1 comma 2.5. All right, and then we want to just keep going with this exact same process. And here, let me go ahead and maybe highlight some of these things so that all of these things match up, right? And then we had purple for this other one. So this, yikes, purple there and this purple here. Okay, make it nice and visual. All right, now we're going to do our third iteration here. We're going to take the previous x value. I need another color. How about green? This 1. Add in our step size of 0.5 to get 1.5. It's that value there. We're going to take the 2.5 from the previous y value, 2.5. How about night blue? This 2.5, that's going to be the same thing, 2.5 there. Plus our step size of 0.5, and then the slope used at our using the previous point of 1 comma 2.5. 1 plus 2.5. All right, so that's going to be a 3.5. 3.5 times 0.5 gives me 1.75 plus 2.5 gives me 4 1/4. So our new point here is 1.5 comma 4.25. All right, and then we just have to do this one more time and we should be able to get to our last point. But before I do that, let's highlight a couple of more things. And then let's see, we had green for that x value right there. All right, so we just need to do this one more time. I ran out of room. So again, this is the x sub n and the y sub n. So I have to use the previous x value, which is 1.5 here. Let's see, it's going to be teal. And I'm going to add that in to the step size, 1.5 plus 0.5 to give us 2. And that's exactly where this problem wanted us to go, right? So this is, in fact, the last step. What was that, teal? That's a really nice color. I should use it more often. Okay. Now we're going to use our previous y value, which was 4.25, 4 1/4. And it's going to get this kind of pinkish salmon color there. Okay, there you go. That's this one, that's this one. Plus our step size times the previous slope at this point, 1.5 plus 4.25. Maybe highlight some things. That's this 4.25. Don't forget about your teal. Lovely. All right, so let's 1.5 plus 4.25 gives us 5.75. Multiply that times a half of that step size. Add that into 4.25, our y sub 3, really, and get plus 4.25 gives us 7 using the highlighter. Way to go, 7.10%. Hopefully I can finish this video. 1, 2, 5. In other words, y of 2 is approximately equal to 7.125 by Euler's method. Can I get a better approximation? We sure could. We used a step size of a half, right? We used a step size of 1/2, but we could have made it better if we'd used a step size of, say, 0.25. Get a little bit more accurate. I can get as accurate as I want to, but you can see how many more calculations I would have to do. As a matter of fact, this kind of stuff is carried out pretty easily, though, with a calculator program. And there was that calculator program that I showed you on my website. So let me just flip back briefly to the slideshow here. And then here's all of that stuff that we just did. Look at all this math that we just did. It looks like we got it all right. Yay! And here's what it looks like if we chose a step size of 0.25. But notice that this one only goes to an x value of 1. An x value of 1 gives us 2.882 blah, 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 blah. Let's compare that to our x value of 1 on this previous example, which was an x value of, was it 1 or? Yes, at 1, right here. It's this green one here. It gave us 2.5. And so this is just a little bit more accurate at that particular point. Okay. All right, the last example is something that I sometimes have to do, especially on a free response question, and kind of another follow-up question. Given that y of 0 is equal to 1 and dy dx is equal to x plus y, find the second derivative. And for some reason, there's a question mark there. Determine whether the two previous approximations are greater than or less than y of 1. When they say that, that means the actual value of y1, because all we've done is just kind of approximated it, and then explain our reasoning. Okay, so let's just take a look, do a little bit of computation here. There's that example and the other one. And ignore the picture that we have right there, which is basically telling us the answer. We want to find the second derivative. And now this is going to be like implicit differentiation. The y that's up here on the top tells us that that is the dependent variable. Any dependent variable needs the chain rule. Any independent variable, which is the stuff that's on the bottom here, that's the x, it's differentiated normally. So d2x y dx2 should be equal to the derivative of x is 1 plus the derivative of y is dy dx. And you might remember from our lesson on implicit differentiation, now what we do is we take this x plus y, which is equal to dy dx, and plug it in right there. So this is 1 plus x plus y. So there's what our second derivative amounts to. And what does our second derivative tell us about our curve? It tells us about concavity. And remember what we're basically doing here with Euler's method is that we're using tangent lines. And concavity tells us where those tangent lines are. If our shape is concave up, then our tangent line is going to appear down below and it under approximates. If our shape is concave down, on the other hand, then our tangent line is up above and it over approximates our function. So that's the judgment that we need to make for this particular function. So what I'm going to do is just take a look at our initial condition here of y of 1 is equal, or y of 0 is equal to 1, and our step size was a half, or it was a quarter. It's moving towards the right. This is in, yikes, this is in the first quadrant. Our entire solution takes place in this first quadrant, where x and y are both positive. Okay, so now put that together with what we have here. What kind of number must that be? If x is positive and y is positive and we're adding 1 to it, that means it has to be greater than 0. If it's greater than 0, this means that our function must be concave up. If it's concave up, then our graph looks sort of like this. And Euler's method is generating tangent lines that appear below our shape, and this is going to under-approximate our actual values. It's going to be less. So as far as me writing this up, I'm going to say something along the lines of the two previous approximations underestimated the value of y of 2, I think it was. That's what we're looking at. And I need to justify that because, or since, or something like that. Let's see, we need to be able to say that this thing is concave down, and the way that we're going to do that is just say that d2y dx2 is greater than 0. It's positive for x and y greater than 0, which is the solution. This is the quadrant in which our solution takes place in. And that is a more than adequate explanation of why we have just underestimated the value of the actual function at those particular points. All right, that's going to conclude our lesson then on slope fields and Euler's method. A slope field, each little point in the coordinate plane, if I take its x and the y coordinates and I plug it into our differential equation, it tells me the slope at that particular point, and I highlight it with just a tiny little line. Taken together, it gives me a way to visualize what a solution curve could possibly look like given some sort of initial condition. And the second objective here on Euler's method gave me a way to approximate solutions to differential equations to any degree of accuracy using some step size, and then the information from the previous step, the previous slope and the previous y value.